And now there is a twist to the REL MAE, which is the MASE. The MASE is a mean absolute scaled error that was proposed by Hindman and Köhler in 2006. It is defined as the MAE divided by the MAE of the seasonal naive forecast over the training part of the time series, right? So in a sense, it's REL MAE, but instead of this quantity by which you divide, it's not from the test set, but it's a quantity from the training set, right? And that now has the advantage that your training set is usually a lot bigger than your test set. So it's not going to degrade to be just the size of 1 and things like that. Yeah, and then actually afterwards, so not in this original paper, but afterwards people have defined the RMSSE, which is the equivalent just with squared errors. And that's a measure that was used, for example, in the M5 competition. Yeah, so these measures, they resolve many problems that all the other measures that we've seen so far have. So they are minimized by the mean or median of the forecast distribution. They are scale-free. There are hardly any problems with zeros or intermittency, because you only divide by a 0 if your whole training set is 0. And if your whole training set is 0, well, your forecast should probably be a 0 as well. They cope well with many types of non-stationarity. Yeah, because the remainder of the benchmark needs to be stationary for the estimator to be consistent, right? And so what that means is that when we use naive, the series need to be different stationary, right? So we are using here, I mean, again, here we are plugging in, so this is the forecast of the naive method, right? So you could just say, I here have my Y head of some benchmark method. And so by what we divide here, that needs to be stationary, so that the remainder, or the error of the benchmark, well, yeah, and because it's over the training set, yeah, you can say the remainder of the benchmark should be, needs to be stationary to not have these problems that I've just shown you in the WAPE. Yeah, which means that if you use naive, well, you are effectively differencing, and so these differences need to be stationary. It does have an interpretation, which is that if the MASE is smaller than 1, the forecast is on average better than the naive. But it also has problems, obviously. Yeah, so as with other measures, MASE, RMSSE depend on how meaningful the chosen benchmark is, right? So I've just said about the WAPE, you're effectively using a 0 as a benchmark, and if your model, if your series has like a strong trend, then maybe a 0 forecast as a benchmark is not a good benchmark. Well, the same can be said about the naive as a benchmark. So the naive forecast works a lot better on certain smooth series than on others, right? So if your series looks like this, well, naive is going to be a quite decent benchmark. But if your series is an AR1 with a negative coefficient and it just jumps around like this, naive is going to be horrible as a benchmark. So you will get a way smaller MASE for this first type of series and for the second type of series, just because the naive is a better or worse benchmark on these series. It doesn't really tell you anything about the performance of your method on these series, right? Okay, so yeah, so like MASE and RMSSE have been proposed with naive and seasonal naive. But you could also use more complex methods like ARIMA, simple exponential smoothing, or whatever you think is a great benchmark to use. Yeah, and now another point I want to make is that it can be difficult to choose a benchmark with fixed origin forecasting when we have many different horizons. What do I mean with that? So let's say this is my training set. I have a quite long test set, but fixed origin, right? So I only from here I'm forecasting. So here it's horizon 1, horizon 2, blah, blah, blah. And that last forecast is maybe a horizon 48, right? Let's say hourly time series 2 days ahead, so we predict 48 hours out. And now in the maze, you see, like we choose naive as our benchmark, and that is probably one step ahead naive in the training set. Okay, so now you get a maze that is larger than 1, and you say, oh, hold on, but I just learned that the maze larger than 1 means I'm worse than naive, so is my forecast really bad? Well, you are, if your maze is larger than 1, you are worse than one step ahead in like naive in the training set. So you're worse on average than one step ahead naive. But you are here not doing one step ahead, you are doing 48 steps out. So of course you're going, like, predicting 2 days out is a lot more difficult than predicting 1 hour out. So of course you are going to have a higher error than a naive that has to predict only 1 hour out. So in practice, you very often see MASE or RMSSE that are actually larger than 1. Yeah, and another problem is that the series can have significant changes, structural breaks between training and test set, and then you also get quite unintuitive results. Right, so that's why they are in practice often difficult to interpret, because very often you see a maze of 2 point something, like not between 0 and 1. Yeah, so high or low maze is not necessarily equivalent with good or bad absolute performance. It only tells you something about relative performance, right? Like, if I have 2 methods, one with a higher maze than the other, you know, this method is worse than the other on the same data. Yeah, well, just to maybe talk a bit more about that. So one thing that I'm quite sure we have seen in the M5 are things like you have a new product that gets introduced. So pretty much all of the test training set is 0, and then it starts taking off a bit, and then in the test set it really starts to take off the product sales, right? And so now the maze tells you, oh well, in sample that's super easy to forecast, like my naive has a super small error, right? Average naive error, very small. And then here now on the test set, your method is struggling, you are not getting that right. Your forecast is, you know, maybe under forecasting by a lot. And now certainly your maze for this particular series really blows up, and you get a really high maze just for this series, but not because your forecast is super bad on this series, just because of the difference between training and test set, and that the training set is much easier to forecast with naive than the test set. Yeah, exactly. That makes it difficult to interpret in practice, right? Okay, so now should you use another important question is, should you actually use MASE or RMSSE, right? Because people usually use MASE. So the question is, why did the original authors propose MASE and not RMSSE? Well, so I talked to them, and the response I got was, the original paper proposed MASE to stay close to MAPE so that it would be easier for people to switch. Yeah, and the idea was that the MASE is easier to understand and more likely, yeah, to be adopted. And another important point is that there is no big difference between MASE and RMSSE for classical methods that assume Gaussian errors, right? So methods like ETS or REMA that were the methods of choice back in 2006 when the MASE was introduced. Yeah, but nowadays RMSSE is adequate in many more situations than MASE. It's the same discussion as that you could have with RMSE versus MAE, that, well, MSE has just some statistical properties that are very nice that the MAE doesn't have. Yeah, I don't want to go into too much detail here, but basically RMSSE is the measure you should usually use unless you have good reasons to use MASE. Okay, So now to summarize the discussion of the error measures and to give some recommendations. So in this paper that I talked about earlier, which is a forecast evaluation for data scientists that I wrote together with a PhD student and another collaborator, there we have this table here, where we kind of just try to summarize a bit when can you use which measure and when you really shouldn't. I mean, I guess the recommendations have evolved a bit. So I mean, here we say, well, if you have count data that are far away from 0, you can use a MAPE. And yes, you can, but probably you still shouldn't, and there are probably still better measures out there. But yeah, so this is kind of a bit of guidance. Yeah, and just to summarize, so to get a scale-free measure, we need to divide by a normalizing factor due to the potential non-stationarity and non-normality, like intermittency, for example, of the series. It has turned out to be extremely difficult to do this in a way that always works for every time series, every size of test set, every configuration that you run. So today, RMSSE and MASE are really the standard error measures. They have been used in M5 competitions. They solve many problems that these other measures have with non-stationarities and so on. They do have problems with structural breaks between training and test set, and they may not be very interpretable, especially with long horizons or fixed origins. Yeah, so it really depends on the characteristics of your data, which measure will be adequate. So yeah, let's go to some recommendations. So if you currently use the MAPE or the SMAPE, you should switch to something else. Do not try to invent your own measure. It will be much more difficult than you think. Some people, namely Stefan Kolassa, argue against using multiple measures. And well, they have good reasons for that, because different measures are minimized by different summary statistics over the forecast distribution. Right, so if you want the mean of the forecast distribution or the median, you need to just use different loss functions and then evaluate accordingly. And then evaluating for both, may not be the best idea. But my take is basically you choose what is your primary metric, could be RMSSE. Then you choose a loss function for that. So RMSSE is a squared metric, so you want to use a squared loss, L2. And then you calculate some other metrics kind of just for sanity checking, right? So I mean, I think it is quite interesting to know that if you use MASE, you get kind of the same result. So if you use MASE now, suddenly it's all totally different, right? I think it gives you some additional information. Okay, so when you build a global model, then often the series actually do have meaningful scales. It's all SKUs, it's all dollars, it's all, it's all something. So then you maybe don't need a scale-free measure. And if you don't need one, then really just better stick to MAE, RMSE, because you don't have these problems that you have to divide by something. And then under certain weird edge cases of non-stationarity, your measures just blow up. Yeah, you don't have this problem then. Yeah, but if you do need a scale-free measure, now the question is, well, so if you will benchmark different methods broadly to conclude which one is best, but you don't need interpretability, right? You only need this relative performance between methods. So this is actually the standard scenario for scientific papers about forecasting methodology. Then I think really RMSSE is the method of choice. And you should use MASE only if there are reasons to elicit the median of the forecast distribution. And also if all of your compared methods are compatible with this loss, right? So if you evaluate over a mix of methods and some are trained with L1 loss, some are trained with L2 loss or similar, like maximum likelihood under certain distribution assumptions, it's probably safest to report both MASE and RMSSE. Right, so one thing that we recently see quite a lot with foundation models is that they only report MASE, but then they win against ETS and ARIMA, which are trained with something similar to L2 loss, so they will perform better under quadratic loss. So that's problems to watch out for. Yeah, now if you need a scale-free measure and interpretability, now it becomes a bit more difficult. So I mean, my recommendation would usually have been use WAPE and WRMSPE, and if you need the bias, the WBPE. But you need to proceed with caution in the sense that you need to have an idea of what's the non-stationarity in your data. And now just some kind of ideas for future work. Well, and I've just said, don't invent your own measure, right? So these are now exactly these examples for, well, I'm kind of coming with my own measure. So I'm just putting this out as ideas, but you really need to, like, they need to be properly researched with simulations and so on, because my experience is that any measure you come up with, it always has these unintended consequences, unintended things. So you need to be very careful. But two ideas I want to put out is, so one is quite simple. The WAPE and similar measures, they could also be normalized just with the sum over the training set instead of the test set. I mean, it doesn't really fix that problem of non-stationarity if you have a strong trend already in your training set. It doesn't really help you, but it could be a good idea in between summing over only the test set or summing over all the series. Well, maybe you run it over the training set. Yeah, and another idea would be, well, I mean, if you really have a long test set, right, a big, large test set, then, well, you could do RMSSE and MASE, but with the denominator running over the test set, and with the same fixed origin setup for your benchmark method, right? So you do, well, this is now a rel MAE or rel RMSE. But the idea would be that your benchmark is not just kind of one step ahead on the test set, but your benchmark is exactly the same configuration as what your method is. So if it's fixed origin with a long test set, you do naive fixed origin long test set. That will make it interpretable in the sense that if this measure is larger than 1, you are really worse than the benchmark. And yeah, again, if you have a large test set, long horizons, this should work, but not in the general case where you may have a test set that is only one value. Okay, that's it for the error measures. Thank you. The next one section is about probabilistic forecasting. Thanks.